Hello everyone, this is Dr. Ian. For today, we're going to be working on circles and finding solutions on problem solving involving the parts of circles. We are more familiar with the two formulas involving circle, which is finding the area and finding the circumference. And sometimes we get confused as to which one is 2 pi r or pi r squared, but we know that to find the area of a circle, the formula is pi r squared, and for the circumference, it's 2 pi r. And for today, we're going to be working on different parts of circles that's not limited to its circumference or problems involving finding the circumference and the area of a circle. So the parts of the circle that we're going to be working on will be the diameter. And we know the diameter would be the line that is connecting our points in a circle that is including our center. So let's say we have center P and we have our endpoints for the line segment that will cross point P or the center. This will be the diameter of our circle, which we will call as line segment AB. And this is also the length of our line segment AB for this particular illustration. And another part of the circle that we all know will be the radius, and the radius, as we know, is half of the diameter, and by definition this is a segment that has one endpoint at the center and the other endpoint will be on the circle. So if we're going to be connecting point P, which is the center, and point A, which is on the circle, line segment AP is going to be the radius of our circle. So this is how we illustrate and define the diameter and radius of our circle. Now the circumference, as we know, it's also the perimeter of the circle. So if we measure the length around our circle, this is going to be our circumference. And these are the three major parts of our circle that we all know. Now, when it comes to measurement and angles involving our circle, we'll be able to define them and illustrate them by 1, the semicircle. And we know that the semicircle is half of the circle, and we know that if we have the diameter kj, which is our line segment connecting the endpoints and the center of our circle, if we move around this particular circle that will connect point K and point J, this is going to be the semicircle KJ that we know. And if we have a semicircle, we have the minor arc, since we are working with the arcs of the circle, which is basically the curvature of our circle. The minor arc is defined as an arc that is smaller than the semicircle. So how are we going to illustrate a minor arc? So let's introduce another point, which is point M. So point M, if we get rid of this semicircle and connect point M and point K, we'll be able to produce our minor arc MK. Now notice the symbol that we are using, because in geometry it's not enough to learn the formula and use the formula to calculate problems in mathematics. We also need to know how to write and read symbols in geometry. And this is how we use the symbol for arc in a circle. So this is our minor arc, and of course, we also have the major arc. The major arc is the larger arc that is, in comparison to a semicircle. So if we're going to get rid of arc MK and connect MKJ, we'll be able to produce an arc that is larger than the semicircle, and we can call this as a major arc or arc MKJ. So we can use 2 letters or 2 endpoints, or we can also use multiple endpoints or multiple points around the circle depending on our illustration. So these are how we denote the arcs or curves in our circle, and we're going to be using that in our problems in a little while. And one of the theorems that we should remember about minor arc is that the measurement of the minor arc is the same or equal to the measurement of its corresponding central angle. And when we say central angle, it means that the vertex of our angle is the center of our circle. So that means arc RT right here, which is a minor arc, and its angle measure for angle RST is 50 degrees. That means if the measurement of angle RST is 50 degrees, the arc measure of arc RT is also equal to 50 degrees. So this is the theorem that we need to remember when we are working with some of geometric notations and problems, and we're going to be using that in a little while. Now, this is how we denote arc measure. So arc measure of arc RT is 50 degrees, denoted by the letter M right next to our arc RT. And if we have the major arc, and if we need to compute for the measurement of the major arc is, we can say, the complement of arc RT. So to be able to find its measurement, all we need to do, and we know that the circumference or the angle formed by the point around the circle is equal to 360 degrees. So to find the major arc, let's say RQT in this example, or TQR, the measurement of our TQR is 360 minus the arc measure of RT, which happens to be 50 degrees. So the arc measure of TQR is 310 degrees. And we know that if we're going to find the value of the arc measure of the semicircle, the arc measure of a semicircle is going to be 180 degrees, because in geometry, we know that a straight line forms an angle of 180 degrees in our basic definition. So this is how we use the arc measure. And again, make sure that you know the notation, which is the letter M in the arc, to denote the measurement of the arc measure of a certain arc. Now, why am I emphasizing that? Because we also have what we call as the arc length of our circle, and this is given by or measured by the formula. We have, let's say, circle O with minor arc AB, and if we want to find the measurement of the length of arc AB, all we need to do is to divide the arc measure of arc AB divided by 360 degrees multiplied by its circumference, which is 2 pi r. And to give a more specific example on how to use the formula for the arc length, again, arc length and not arc measure, we have the circle that we worked on a while ago. So we have a minor arc RT, and we know that the arc measure of RT is 50 degrees. And also, we know that line segment SR is the radius of our circle S. So given by 6 centimeters, we'll be able to compute for the measurement of this arc length right here using our formula. So we already know what the measurement or the arc measure of arc RT, which is also 50 degrees. We are just going to divide it by 360 degrees, and we will multiply it with 2 pi r, which is the formula for the circumference. And the radius value in this circle is equal to 6 as defined in our problem. So all we need to do is, 1, we have an option to use the calculator, or we'll just use our hand to solve this problem. And that's what we're going to be doing in this particular arc length. So we know that the measurement of arc length RT or arc RT is equal to 50 degrees. And by using the formula, we know that we can have 50 degrees all over 360 degrees multiplied by 2 multiplied by pi and multiplied by the radius. And we can, of course, use the calculator to find the value of the arc length RT, but we also know that we can simplify this by prime factorization. So we'll have 5 all over 36 multiplied by 2 multiplied by pi and multiplied by the radius, which happens to be 6, which is equal to 6. And we know that 2 times 6 is equal to 12. And we also know that there will be 3 12s in 36. So that means we can cancel this and we will have 3 in our denominator. So we'll have 5 all over 3 pi as the measurement of arc length RT, and this can also be written in some textbook as 5 pi all over 3. Both of these notations are the same and equal. So if you happen to have this notation or this particular notation in your book, you know that they are just the same. So this is how we find the arc length of a given minor arc using our formula. And we're going to be using that more in a little while. So now let's talk about congruent arcs and how to use the theorems of congruent arcs in some problems involving circles. So congruent arcs, by definition, are arcs that have the same measure and are in the same circle or incongruent circles. To illustrate that, let's have two circles, circle O and circle P. And we know that they are congruent because they have the same measurement. And by just observation, and if we put them on top of each other, we know that they're going to have the same measurement. And if the circle are congruent, its arc measure and arc length are also congruent. So that means arc XY has the same measurement as arc RS, both on its arc measure and its arc length. And that is the theorem for congruent circles in relation to congruent arcs. And we also need to remember that when we have congruent circles, we also have congruent radii, which means the value of line segment PR is the same as the value or the length of line segment PS. And another theorem that we need to remember about congruent circles is that the central angle that we are seeing here right now, the reason why it's called the central angle, it's because its angle or the vertex of this particular angle is the center of our circle. So angle XOY, which is denoted by this notation, is a central angle because its vertex is our center of this circle, which means for circle P, angle RPS is also a central angle because the vertex of this angle is also the center of circle P. So again, it's important that we know the terminologies in circles and parts of our geometric figures so that we'll be able to answer more problems in geometry involving this particular figure that we're working on. So with that, let's take a look at these two circles, and obviously they are not the same. So they don't have the same size of circle, which means circle O is not congruent to circle B, but since we have the same measure for the arc measure X, Y, and AC, does that mean that their arc length are also the same? And we know that if they are not congruent circles, their arc length will also not be congruent. And the reason why it's not congruent, we'll illustrate it with a little diagram. So if we connect center O and center B and draw a line that will pass through O and B, and let's extend or produce another line that is parallel to this line right here, right above arc AC, we will notice that there's still a little bit of space right here that's not covered in our parallel line, which means by just observation and with this illustration, the arc length of AC is not going to be the same with the arc length of XY because it's still missing a little piece right here because we have a bigger circle for O compared to B. So remember, so even if they have the same arc measure, they will, it doesn't mean that they will also have the same arc length because the two circles are not congruent. So circles that are not congruent will not produce congruent arc lengths. So that's what we need to remember about congruent arcs and this theorem that we are using for two circles that are not congruent, which is in this case, since they're not congruent, arc length xy is also not congruent to arc length AC. So now let's move on to this particular problem or example involving a circle with a lot of points and lines in it. So in this case, we know that circle O has a radius of 18 meters and we denote the circle by its center. So we name it after the letter of the point that we are using for the center. In this case, we're using O as the center. So this is also called as the circle O. And we're going to find three measurements. So we need to find the measurement of angle BE, the measurement of arc length AED, and the measurement of arc length DEF. So let's start with the measurement of BE or arc length BE, and we know to be able to solve the measurement of this particular arc, all we need to do is to refer to its corresponding angles, which is angle BOE, and we can easily find it because we know that this is 35 degrees, and also this is equal to 90 degrees. So if we add 35 and 90 degrees, it will equal to 125 degrees. So the measurement of arc BE, which is corresponding to angle BOE, is equal to 125. Now, how are we going to find the measurement of arc length AED? So let's figure out a way on how to illustrate arc AED. So this is A, this is E, and this is D. So if we connect that arc, we'll produce a semicircle, and we know that this is a semicircle even though we don't have a ruler to measure it because of the 90-degree angle right here, and we know that adjacent to it is also a 90-degree angle, and if we add them up, it's equal to 180 degrees. So that means it is a semicircle, and it's equal to 180 degrees for the arc measure of this particular arc, which is arc AED. And now we're going to find the measurement of arc length DEF, and arc length DEF, we have DEF, and we're going to find the measurement of the length of that arc and not its angle. That means we're going to be using our formula to produce that value. So we could use the formula just like what we did on the previous example because we know that the measurement of DEF is equal to 30 degrees plus 90 degrees, and this is equal to 120 degrees. So now that we know the measurement of DEF or arc DEF, we can use the formula for the arc length, which is the measurement of DEF all over 360 degrees multiplied by its circumference. And from here, we know that the radius of our circle is equal to 18 meters, and we are going to use that in our formula in a little while. So the measurement of DEF is 120 degrees all over 360 degrees multiplied by 2 times pi times r, which happens to be 18 degrees. And again, we can use our calculator for this or simply use prime factorization to solve for our fraction. So this can cancel out. So we'll have 12 all over 36, which is 6 times 6 multiplied by 2 multiplied by 18, which is equal to 2 times 9 times, of course, don't forget the pi. So this is our prime factorization, and this will help us simplify our fraction a lot easier without using the least common denominator and the calculator, because we know that 2 times 3 is equal to 6, so this cancels out. 2 times 3 is also equal to 6, so this cancels out. And we are left with 12 pi, which is our arc length, and it has a unit of measurement of m, or meters. So the length of arc DEF is equal to 12 pi meters. So this is how we use our formula, and of course our skill in prime factorization to simplify our fraction. That gives us 12 pi meters. And if you want to see how the formula was used in this particular word or problem for a circle, just remember that it's always the measurement of the arc all over 360 degrees multiplied by its circumference. That is the length of our given arc. And remember that arc measure is not the same as the arc length of a given circle. So this is how we solve problems involving circles, and remember that it's important that we know the terminologies associated with our geometric figure and its parts to be able to understand fully how this formula works and how we are translating those symbols to be able to solve geometric problems like what we just did today. This is Dr. E, and see you again next time. Bye!